Good afternoon, everyone. Good morning to some. My name is Jolene Pratt. I am the Marketing Coordinator for Cadent Resources Group. Here is Mark Avor to present Supply Chain Physics 2, the very real decision space of supply chain physics.
Thank you, everyone, and thank you, Jolene. As Jolene mentioned, please do submit your questions. We definitely would like to have that interactivity at the end of the presentation. Today we're talking, it's a part 2 of this 3-part series, and we're talking about the very real decision space of supply chain physics. And part 3 will be on January 20th, and we'll talk about strategies and communication and improvement. The agenda for today, we're going to go over a recap from part 1 for those that may have or may not have been and seen part 1. We'd like to go through 4 examples to solidify the laws of supply chain physics, and then get into supply chain optimization, discuss 2 categories of supply chain physics violations, and then have the conclusion and Q&A session. Why supply chain physics? As we discussed last time, it's a concept. It's based on science, engineering, and business. And what we're presenting here really is a language and a set of principles to make sure that we have accountabilities across the various functions of our corporations and businesses, and also to foster improvements across that entire organization or enterprise. We found that it's a very useful concept in which to have these dialogues, and after using it, people start feeding back the same conceptual, the laws of physics and the concepts that we talk about. So we're very high at this. Last time, if you recall, we presented a general supply chain model. We had an order taking and fulfillment part of it. We had a manufacturing part. And the key that we wanted to get across from this was that as you go from right to left, from the customers placing orders, the order being processed, released to the warehouse, somehow that orders and future orders being communicated to a manufacturing planning, through purchasing, release of orders to suppliers, that's all flow of information. Going from left to right, on the other hand, you have the flow of goods. You have raw and packing materials going to the manufacturing facilities, value being added and turning those into finished goods, the inventory being allocated to the various warehouses and distribution centers for then picking, packing, and shipping to our customers. So you have material, product, and flow going from right to left, or left to right, excuse me. It's a concept I've had trouble with since first grade. We presented last time 3 laws of supply chain physics: the law of interdependency, the law of constraints, and the law of information. The law of interdependency talked about inventory, service, quality, and cost as being interdependent. At a certain point, when you've improved your organization, reducing inventory may have an impact on service, certainly will have an impact on cost. Raising inventory could improve service, it could have an impact on cost. If you have quality problems, it could have an impact on service and cost as well. In business improvement, the siloed functional improvements can only take us so far. At a certain point in organizational development, you get to the point where further improvement requires cross-functional cooperation, and that's what we're trying to get across with this law of interdependency. There's 2 parts to it. 1, these performance measures are interdependent, and 2, your improvements can only take you so far before you have to work with your co-functions to improve further. The law of constraints. There is a constraint that says how much of any item can be produced in a finite amount of time. There are limits. We have production capacities, we have production rates, all of which have to be adhered to. We have machine downtimes. We have a limited number of machines. of factory tools that we can apply to produce products, a limited amount of labor. How far and fast can the goods be shipped from point A to point B? There is a limit on how fast product can move. As we've elongated the supply chains with many companies outsourcing production to various locations around the world, particularly centered in Asia, the factory that used to be next door to your DC is now halfway across the world. So there's a limit of how quickly you can move product from point A to point B. And we called it the law of constraints because, yes, it is very related to the theory of constraints. Lastly is the law of information. And I think in part one, we talked about the beer game supply chain simulation / game that was created at MIT probably back in the 50s or 60s, and in which we were looking at the constraint there, or the lag time, was information did not move efficiently through the system, and it moved slower than actually the goods moved. I think that's changed now. Information moves at the speed of the internet, if you will, and it's independent, of course, of the accuracy of the information. Bad information travels just as fast as good and accurate information. Currently, I would say in most supply chains that we look at, the speed of information is grossly greater than the lead times, and the speed of information also probably is faster than the production rates. We presented this concept to hammer home the interdependency of this whack-a-mole, supply chain whack-a-mole. You have quality, cost, service, and inventory, and we want to emphasize again that if you optimize all of them to a point, there are companies that probably can still improve quality, reduce cost, improve service, and reduce inventory without having to worry about the interdependency of them. But at a certain point, you get to a level where you've gotten all that you can, you've taken all the slack, if you will, out of those performance measures, and now they become interdependent on each other. So then you have to do trade-off optimization. If you want to optimize all of them simultaneously, again, that would require some structural change to achieve that. Okay, let's get into some examples here. You know, our company, Cadent Resources Group, is, our mantra, our corporate mission is to help companies reduce inventory, improve service, and generate cash. We focus most of our efforts around inventory management and inventory optimization to improve service and in our supply chain practice. So the first three examples we're going to look at, in fact, most of the examples are rooted in terms of inventory as being a primary view. And so please indulge us as we look at this. Example one, it's a simple inventory model, single SKU. You have some kind of safety stock in blue, and you have an order quantity which has been calculated, probably using some sort of formula. Some companies probably guesstimate these things. And in between you have a reorder point. So, you have working stock. When you reach the reorder point, you place an order to replenish the goods, or a manufacturing order to replenish the goods. And as the goods are being produced and shipped or delivered to the Kanban location, which is probably a warehouse, you're eating into the safety stock, and you design the safety stock so that before you run out of goods, you replenish the goods to this amount, and you probably end up with a replenishment somewhere around here. When it gets to there again, you go through this process, and I'm probably preaching to the choir here because it's a very elementary concept. The safety stock is based on what? It's based on manufacturing and transit time variations for the most part. As we mentioned before, there's limited capacity. It takes time to move the goods from the factory that's making them to the DC at which you're storing them. There's variation in that transit time. I've seen companies where we import from Asia, where sometime in January when you get to Chinese New Year, things take longer to get from there to here. It could be at the current time we're at, if you're a few months ago, where the Christmas rush may have made transportation equipment less available. It takes time. So we have the safety stock to protect us from these kinds of variations. Oh yes, I forgot to mention, there's also this thing we call demand volatility. And this is that our demand plans created with the best of science and statistics and the best intents of sales, marketing, and supply chain aren't always accurate, because darn those customers, they don't always order what we think they're going to order or what we try to sell them. So if we break down the safety stock further, we can see that there are demand chain variations. This demand volatility in the darker mauve, I guess it is, and the supply chain and lead time variations. We've made it a 50-50 split here. In a supply chain, we are responsible for these parts that we have highlighted with the arrow. In other words, the order quantity is dependent on the manufacturing capability, how long it takes to get goods. As I said, there's calculations we can look at to establish that. If the factory is next to the warehouse and you have essentially infinite manufacturing capability, that order quantity is going to be very small. If the factory is halfway around the world and you're trying to fill up a container as your primary constraint, you may have that order quantity be higher. Part of the safety stock is definitely due to all those variations that we spoke about. But is the supply chain responsible for this part, the demand chain variations? I'll give the pregnant pause here so you can ponder that question for yourselves. There's probably, if there's any salespeople listening, they're probably going, no, the supply chain is still responsible for that. And all the supply chain people are probably saying, nonsense. The sales guys are actually responsible for that. The commercial side of the business is responsible for that. You probably need to know this breakdown for your companies. We have seen manufacturing or supply chain lead times dominant, making it 80-20 between this and the demand chain variations. But there's also examples we've seen where these variations, and this operates a lot tighter, so it's a 20%, 80% split between these two. We can actually assign an inventory objective to sales. We can actually assign an inventory objective to sales if we wanted to. I had raised this question at a company I'd worked to the division president, a very, very smart businessman, cerebral and practical at the same time. And he told me, Mark, brilliant idea, it'll never fly. And I think he's absolutely correct. We can assign an inventory objective to sales. I guess I'd like to emphasize that point. And someday I'd like to see some company actually do it. And if any of your companies have, please contact me, because I would love to blog that case study a little bit. Okay, so that's example one, is that at a certain point, inventory improvement is going to require us working with the commercial part of the business. And what do we mean by that? I mean, this is where reducing the number of SKUs comes into picture. This is perhaps reducing the number of customers. At what level do you want to aggregate your business planning, et cetera, et cetera. Okay, example two, E&O inventory. E&O is kind of the general industry term for excess and obsolete inventory. Excess is the inventory that you're still selling the product, but you have way too much of it. The threshold there is usually 3 months of supply. Forward-looking, you say it's excess inventory. Obsolete inventory means I've got this inventory, we don't even sell the SKU anymore, it's just sitting there, there's no hope of selling it unless we do something special. I actually like the term SLOB, slow and obsolete, because SLOB is a nice little acronym there that actually conveys what it is. It's slovenly, it's not organized, it's slow and lethargic, and it evokes all those good images. So I really would like to have everybody call it slob, but E&O seems to be the inventory term. These inventories result because of two things. The demand planning or forecasting errors and the historical violations of the laws of supply chain physics that we talked about. You are tasked as a supply chain leader with reducing E&O, which is 20% of all the inventory at your company. We have actually seen companies that have 60% E&O. 60%. I would slip my wrist if I had to operate in that situation, but there are people that do it. Let's just say you got 20, and let's say you have an objective to cut that down in half. Yet, as a supply chain person, you're supposed to do this, but you're not allowed to write any of it off because you just don't have the permission to do that. And the goal is to sell it at full margin, i.e. no fire sales. This is a very real scenario. I've had this scenario in two different major global corporations that I've worked at. I've been tasked, reduce the E&O, but you can't write any of it off, and you have to sell it at full margin. I'm like, okay, I understand what you're saying. No one has ever been able to explain why and how this is tasked to the supply chain. How is that possible? You can't sell it, we can't dispose of it, and yet we have to reduce it. And the thing that I practiced the speech, and I learned it very quickly and early, was that you've tasked me to do this. I can't sell it, I can't dispose it, I can't reduce it, yet all I can do is neatly stack it up, and I have to dust it off now and then because it really can get dirty if it's been sitting there 6 months, a year, or longer, and report on the value of it monthly. And as I said, this is a very real scenario that's happened to me personally, and I know other supply chain people are probably saying, yeah, shaking their heads in affirmation. So that's another example. That's the law of interdependency. You can't. How do you get rid of this? Well, if you can't sell it, you need the salespeople to help you sell it. And if you're going to sell it at lower margin, or you're going to write some of it off, guess who you need there? You need finance to participate with you in order to be able to do it. So it has to be a coordinated effort. You've gotten to a certain point of your optimization or your supply chain optimization where now it's required. The law of interdependency kicks in. If you want to do things, it requires the cooperation of other functions. Example 3. This is good because not all examples are necessarily violations or horror stories. There are some good examples. And this is a CPG company I've worked for, and the last 2 companies I've worked for are CPG companies, so you could probably narrow it down by looking at my LinkedIn. There was a strategy that this one company had. A new general manager comes into the subsidiary, and both these companies were organized by subsidiaries, so it was, name the country, and that was a subsidiary. The new general manager comes in. He's absolutely, totally shocked by the level of E&O. He says, he disparages the old general manager. He says, how the heck did this happen? I can't believe that guy let this happen or that lady let this happen. And that person obviously has probably been promoted to a larger subsidiary. So the new general manager comes in, clears the deck, has a fire sale, writes off stuff, throws out all the old junk, and then spends the next tenure, the next 2 or 3 years of his tenure as general manager of this subsidiary, building E&O back up, and the cycle continues like that. So he comes in, he's shocked, he's horrified, eliminates all the E&O, and then rebuilds it during his tenure because it affects his quarterly and annual performance if he does any of the fire sales or write-offs, and no one wants to do that. In one of the Latin America subsidiaries, in this case Argentina, and we may actually have one of the participants on this call is well versed with this, having worked at that company in that subsidiary. We got a general manager that came in there and realized it was not a supply chain problem alone, but something that was shared with sales and finance. They assigned 2 people to work on this, an inventory czar to work on inventory in general, and a salesperson focused only on selling out the E&O that could be sold. The analysis showed that underselling or overproducing promotions was the largest cause of E&O, and mostly it was underselling. But there were also cases of overproducing. 10+% was an obsolete alone, and so the attack here was a two-pronged attack. And we want to look at better promotion planning and execution and putting in some performance measures to ensure the execution. And then, so that was a strategy not to create more E&O, and then for the E&O we had, selling it off. Better promotion planning and performance measures, we tracked demand plan versus actual by account. Before it was just done on general. Now we're looking at account. So we're saying which sales guy said I was going to sell 100 and I only sold 50, or I was going to sell 1,000 and I only sold 500. And manufacturing committed to having the promotion if it was a special package, that required a 2-for-1 pack, or a special promotion that required a different packaging, to have the promotion ready to go the first day of the month that the promotion started. Then we would check mid-month the account forecast versus sales to see how was the promotion going, if we needed to light a fire underneath any of the sales guys, or maybe even reduce prices anymore to make sure that we sold all of it out. This practice that was started in this subsidiary, and then it was copied at other subsidiaries as well, led to the co-development of a promotions management module with the ERP provider at that company. And I think they're still using it. In this example, marketing folks but it's always something I wanted to do. All right, selling off the E&O. How did we do that? How was this done? Well, in a warehouse, we created a space for the saleable, and not all product was saleable. The product that wasn't saleable, you had to make the decision, the hard decision, to write it off. We created a space called the E&O showroom. Old promotions were to be considered in the new product, any new promotions that were being planned, and the salesperson that was assigned to this had a meeting with the manager. It was a quick meeting, not very long, to review the offerings every month, and he would take some of the offerings to the meetings to say, hey, we have this stuff, can we use it? In consumer product goods, you have trade promotions, which are not necessarily special packaging, but you say, okay, this month only, or 10 days this month, we're selling, you buy 2 cases, we give you 1 free, a buy one, get one offer. We raised the question, and it became practice that why offer a case of the same product that they were buying 2 of? Let's give them a case of the E&O. And of course, it was only a good promotion if it wasn't really a dog product that you're trying to pass off. It had to be something of value, but that's another way of getting rid of some of this E&O. And we needed finance to sign off on the promotions just to make sure that the margins were intact and everything was cool there. Example 4 is more of an example of the law of constraints and information. Let's look at an aggregate product category. This is a company that Cadent Resources works with now, and this is an output from our demand caster software. Every year, if you look at 2007, demand goes down. 2008, demand goes down further. The green is the actual, the red is the forecast, the blue is the forecast into the future. It went down, last year, at the end of the fourth quarter of last year was the start of the recession. Things went down further, so we're operating at a lower level for a while. All of a sudden this year, we're expecting a downturn. What happened? actually demand went up. So this year there's big spikes happening where normally we had downturns. Why is that? Well, the 2008 drop was probably larger because of the recession or downturn, and the company and a lot of companies all over the country had to scramble to downsize inventory. Now in the fourth quarter of 2009, I don't know, are we coming out of the recession? Are we returning to a pre-recession level of demand? We can't tell, but we're seeing spikes in demand sporadically and within companies that we work with, and anecdotally we're hearing from other people that we meet at professional meetings and talking to in general, that these spikes are happening within lead time for product produced in Asia. The company can't react fast enough. This is what we're seeing and hearing. So if we look at, here's an example, and this is not the example of the picture we showed, but let's say I buy myself for a Christmas gift, a holiday gift, a camera at Best Buy. And it's very interesting. Here's a case of the information can go from the Best Buy store in Vernon Hills, Illinois, where I bought it, to the local planning center. Maybe it's the National Planning Center. That is consolidated into some sort of forward forecast that's communicated to the factory in Asia, and they communicate that to their suppliers. Easy to do. Very fast. That's the speed of the internet. Now, let's go the other way. I have to get components from these sub-factories, maybe a raw component or a base component going into a sub-assembly that goes to the factory, that goes to the distribution center, that comes all the way around the world, and they probably wouldn't go this way. As a logistics expert, I would recommend they go. They would head towards California from across the Pacific, and then it gets shipped to a distribution center perhaps in the Midwest, and then to my local Best Buy store, and I get the camera from there. While the information was almost instantaneous, lean, and it could be a very lean operation. Lean is not just in time, and that's something that we're going to probably talk about maybe in another webinar next year, the difference between lean and just in time, because that's a critical difference. You cannot react to demand spikes or changes within lead time, and if the lead time is weeks, it takes like 30 minutes to make the product, maybe for some of the components, and sometimes we've seen chips take as much as 6 or 7 weeks to get for assembly like that, and then it takes like another 4 to 6 weeks to ship it, and all of a sudden if you minimize your inventory last year around this time because you were scrambling to try to reduce, now all of a sudden you're scrambling to try to recover, and you're out of stock, and customer service is suffering, and sales are suffering. You can't react fast enough because of this grand distance. Here's a different product category. We see the same issue. This one it's very similar. Downturn in 2007, downturn at the end of 2008. We're operating at a lower level. All of a sudden, 2009, we see a sharp increase in the fourth quarter, a big spike in actual demand, and all of a sudden we're forecasting in the future the inventory, the demand levels that we had before the downturn. We don't know, because it's still predicting into the future, whether this is going to happen or whether it's going to settle back down to this level. Interesting. In one SKU, there were 2 big spikes. It was an overseas vendor. The vendor stated a lead time. The vendor had a lead time that says 75 days will take you to get the product. The company planned a lead time of 120 days to give them some cushion and part of their safety stock. The actual lead time this year has been 133 days. They have not rectified that with they had not talked to the vendor and rectified it because sales were going down. It probably really didn't matter. All of a sudden, you have this spike. Your system is not designed to work. You go out of stock, and you can't react fast enough. You're air freighting, you're expediting things to get in. And here's the cost differential if you want to look at this with these 2 large spikes. You had at 120 days lead time, that's our base. Let's say the impact is 0. At 133 days, you'd have to carry about $12,000 more in stock. This is not a huge product. Or the impact would be 12,000, and at 75 days, you would have been able to save $70,000 in your planned inventory if you could actually operate at that level. And if you didn't have these spikes, you could reduce that even further. You could reduce that to $85,000. You would have $85,000 in inventory savings. It's very interesting to look at these kinds of things and look at the spikes that you have. Are these planned spikes? Are these not planned spikes? You have this base kind of level of demand, and then you have this spiky demand in here. We're looking at ways of actually trying to forecast these spikes, because if you can predict that a little bit better, you might have a better chance of planning how much inventory to carry. All right. Summary of our examples. We believe that inventory and service are the final measures or arbiters of supply chain performance. They are the indicator of a company's operating practices and procedures, good or bad. If your inventory is good and your service is high, you're probably operating very, very well, or you have customers that have very static demand. As we mentioned before, and again a point we're hammering home here, siloed improvements only take you so far. Once you get to a certain level, cross-functional effort is required when the interdependent level is reached, wherever that is. Okay. Allow me 1 second to take a sip of coffee here. This is a 5-second coffee break. Okay, supply chain optimization. The question is, isn't there a lot of math in physics? We keep talking about supply chain physics, and we've hammered home the point that it's conceptual. But let's step back from that conceptual a little bit and kind of brush up against the mathematics if we can. When we violate the laws of supply chain physics, we compromise inventory, service, quality, and cost. These things affect inventory affecting cash and profit, service, customer loyalty and revenue, quality would be customer loyalty and profit, and cost certainly would affect profit. When we violate the laws and compromise these things, we compromise overall performance of the organization. If you don't account for the realities of supply chain physics in these areas, you will compromise and cause trade-offs in these areas. And what are the things that are controllable that we're talking about? Manufacturing lead times, transit times, production rates, capacities, warehouse utilization, transportation, equipment availability. That's more important at the end of quarter, end of year, peak transportation periods. And let's not forget demand volatility. It is a complex multi-criteria problem. You can look at it by SKU, but if we want to optimize it over all SKUs, I being the SKU number, and so we want to optimize cost, inventory, service, quality. There's probably more. You could argue, are these the 4, are there 6, or do we only worry about these 3 and this is a consequence, or do we only worry about quality, inventory, cost, and service as a consequence? That's things we'll discuss a little bit here. Manufacturing lead times are, and subject to, these are all constraints. Manufacturing lead times have to be greater than how much of that SKU you can produce at plant or supplier J. Transit times, moving SKU I from plant or supplier J to DC number K. Production rates, production capacities, warehouse utilization, the same things that we talked about. It's really a multi-criteria optimization problem that we're trying to work with. And what is multi-criteria optimization? What are we talking about here? This is that whack-a-mole stuff. If you go back to that whack-a-mole picture, we can optimize human beings mathematically. We can optimize in one dimension. When you have 2 or more dimensions, it becomes a very complicated operations research kind of problems. And you have to ask the question, are the criteria even independent or dependent? we've got the balance of the scale because it truly is a balancing act. How is this done mathematically? Well, if you had taken an operations research course somewhere way back in your history and remember anything about it, you probably didn't study multi-criteria optimization unless you took some advanced courses. But the way they do it is a couple ways. You can prioritize and optimize each of the objective functions, and the objective functions are the things at the top. These are the objective functions. I want to optimize cost, inventory, service, quality. I can optimize them one by one. Let's optimize quality first, cost second, go right down the list. That's not the most efficient or effective way to do it. There's something else called the efficient set, which we're not going to get into it all today, but if you want to email me about it, I can send you something you can read. The ones we want to talk about are 3 and 4. Map the criteria into one dimension and change some of the criteria into constraints if you can. Well, mapping the criteria into one dimension, and I'll just mention real quickly for those of you that have ever done a Taguchi experiment in your manufacturing background or your quality background, Taguchi, the Japanese quality engineer, came up with an objective function that could take multi-criteria into one objective, and he called it the signal-to-noise ratio, and that's all I'm going to say about that. But if we look at further, one way of taking various dimensions and making it one is to look at money. Money is very additive. My money and your money becomes our money. We can add up revenues and costs across various functions and parts of the business, across the supply base, even through to the customers. We can minimize the costs in the supply chain, and we know pretty well that if we subtract costs from revenue, we can then get profit, which we can try to maximize. And so money is a very unifying dimension, but it's not always hard to quantify things in a dollar-wise. What's the cost of quality? Very hard to measure, for example. So that's a tough thing to always do. But if you can get it in terms of money, that's one way of taking multi-criteria and making it into one dimension. So if you just try to minimize costs and you have cost equations for everything, that'll work. Another way is making some of the criteria constraints. We do this in inventory management, and it's really a basic way of doing it. We want to, let's just look at 2 dimensions of the 4. We want to maximize service and minimize inventory. They're very different units of measure. Service is percent case or unit fill. Inventory is in units or dollars. Ideally, we like to get 100% service, but most people can't afford that level of inventory. So what do? We prioritize our SKUs that we want to set the inventory levels at by ABC classification, and we set some minimum service target levels. In other words, we turn service into an objective, or a constraint, excuse me, from an objective or an objective criteria into a constraint. Here's the formula a lot of people use. ABC classification, it's a top-down classification of SKUs by either sales or margin, and your A's account for 80% of your sales, and in the Pareto world, that's probably only 20% of your SKUs. B's are the next 15% of sales, and C's are the bottom 5% of sales, which often number 80% of your SKUs. The bulk of your SKUs are probably down here and they account for only 5% of the sales. You attach a minimum service level. You want your A's. You always want to have those because they're 80% of your sales in either sales or margin. And so you want that service level to be high. You set that somewhere around 99% or higher if you can. Your B's at 97, your C's at 95. If you're out of stock on these, it's not going to kill you that much. So that's one way of looking at it. And that's a way you turn an objective criteria to a constraint. And that's done all the time in inventory management. One thing our company is looking at, Cadent Resources is looking at, we've taken a 3-dimension product segmentation, and it's coming out in our next release of our Demand Caster software. We're looking at the classification of ABC, certainly, but we're looking at the order frequency, high, medium, and low. And we're also looking at this concept that we've stumbled across and makes a lot of sense to us, forecastability. We're probably going to have a webinar in February we're thinking about just centered on explaining how all of this kind of works. This is really kind of an intriguing concept. And this idea of forecast stability. I mean, you can do your best forecast and it's still, your MAPE is horrible, and you wonder why are we even forecasting it? What can we do about that? So that's something we're going to talk about later. Multi-criteria optimization is hard to do as pure mathematics because it's close to impossible in an industrial environment like most of us work in to get the equations well defined. Things are constantly changing. And as we had said in Supply Chain Physics 1, here's what changed. We're in a world of constant change. We have new supply sources, which changes all the lead times and all the production capacities. We have material and commodity pricing, which goes up and down. We have competition introducing new products that may make the sales of our products go down or up, or we might introduce a new product and then find out we've gained in market share. There's economic factors. I mean, think of the example we showed, fourth quarter of 2008, where everybody's scrambling to reduce inventory, and now where we're starting to see examples in the fourth quarter of 2009 where people are scrambling to try to make up and increase their inventory levels. Technology changes, making information flow even faster and more efficiently. So it makes for a world of constant flux. So we use a combination of math, physics, and heuristics to try to do this optimization. And a lot of it ends up being heuristics. There's a science of inventory management and there's the art of inventory management. And that's what we do as a company, and that's what we use our DemandCaster software tool. It has a combination of all of these things. All right, the next step, and it's kind of a segue into Supply Chain Physics 3, there's two categories of violations. Consider this, that which maybe can be done, because we have the three laws of supply chain physics, so we have three types of violations, the law of interdependency, the law of constraints, and the law of information. But now each of those there's two categories of violation for each of those. We try to do something maybe can be done, and we try to do it, and there's things that are clearly impossible to do. Can't get there from here. These are often violations more so in laws of constraints and laws of information, as you see. That which maybe can be done. It's not necessarily impossible, but it requires a heroic effort, and usually a heroic effort of epic proportions. Most of it, if you have any chance of succeeding or succeed partially, you'll have some sort of whack-a-mole type trade-off on the performance measures of quality, cost, inventory, and service that we talked about. Now, the impossible to get there from here, you're tasked with it's the end of the quarter, end of the year, we got this large order, and you just have no chance of doing it because even if you had a chance, the machine is down, impossible to do. The question you ask then is, of the person asking you to try to attempt to do this, I say, are you freaking kidding me? How did you ever get into your position? And remarkably, how have you kept your freaking job? And I probably wouldn't have used the word freaking. I would have probably inserted another F word there. But that's what I say on the inside because, I'm the meek and mild supply chain guy. What we do is we calmly, clearly, politely explain how, no way we can get there from here to there. From here, and here's the best that you can do right now given and we can communicate this very clearly in terms of supply chain physics. So the question is, when we are convinced ourselves that it's impossible, we can communicate this very well. The laws of supply chain physics are very, very clear, and we have great authority when we explain that to our business partners. That which maybe can be done, I don't know. We can never communicate this very well. And why is that? Because we're good corporate citizens. We're businessmen like everybody else that's in this trying to make sales and make numbers end of quarter, end of year. We're paid to get things done. And generally, you don't get into a high supply chain position unless you have a can-do attitude. That's why when it gets iffy, it's hard to communicate. We can communicate definitely. Yes, definitely no. Maybe it doesn't fly so well. 20% probability of achieving it, well, how do we know it's 20%? We don't know because we don't have the equations. We can't effectively measure it all the way. So we're going to explore these categories in a bit more. and discuss that in Supply Chain Physics 3, which will be January 20th. So that's the presentation essentially for today. What do? We reviewed the concepts of supply chain physics. We presented, or brushed up against the presentation of a mathematical optimization model in concept and strategies for taking multi-criteria optimization and turning it into something we can deal with. In the case of inventory and service, we showed how we try to optimize inventory by turning service into a constraint. And we looked at, well, there's a typo here. We looked at 4 examples, not 5 examples, all centered around inventory. And we set the stage for Supply Chain 3 by talking about those 2 types of violations. And then, so in Supply Chain Physics 3, we'll talk about strategies for communication and improvement. One of the things we have to figure out how to communicate better is those iffy situations. Because in an iffy situation, all people hear is, yes, we can get it done, and then what happens? Maybe if you don't achieve it, you get dinged in the next review, and your performance measures go down. So let's take a look at some of your questions that you've submitted, and we'll invite Jolene to jump back on the presentation here.
Hello. Yes, at this time, if anyone has any questions, go right ahead and raise your hand, and we'll go ahead and unmute your line, and you can ask your question. Again, if you prefer to send a question to me via the question area, you can feel free to do that as well. Mark, I had one question that came across while you were doing your presentation, and that was from Dave Kaminsky, and he says, this forecastability concept is very interesting. Can you talk about this more?
Yeah, that's a great question, Dave. Thanks for asking that. Forecastability, and I wouldn't have known what that meant even a couple months ago. My partner, Ara, came across a great little paper that explained what it was. And you look at forecast performance in terms of MAPE, and you look at the correlation coefficient, the R squared of actual versus forecast for a particular time series. And between the 2 of those, you say if the correlation coefficient is high and the MAPE performs very well, in other words, it's a good forecast, you have an SKU, you have a time series that's forecastable. In other words, you can always forecast the mean, and these are both measures of standard deviation. So if the standard deviation of the forecast and the standard deviation of performance to forecast is low, then you have something that's very forecastable, and you should try to use sophisticated statistics to do it. Now, on the other hand, if they're low, you know, if it goes the other way, your forecast error is high, your MAPE is performing badly, and your correlation of coefficient is low, what do? Well, spending time in sophisticated forecast probably isn't going to help you. Probably the best thing to do then is just use a simple moving average or 13-week moving average. So that's in our new release of DemandCaster, which is coming out. We're incorporating some of this where companies can look at these 2 factors and can dial in those other 2 dimensions in that forecastability ABC classification cube that we talked about. And as I mentioned earlier, we're probably going to have a webinar dedicated strictly to that subject, perhaps in February if we can. Thank you.
Let's see. Again, if you have any questions, go ahead and raise your hand. If you're not sure of the area that I'm speaking of, just go ahead and send me a question. I have one more question that came through, Mark, and that is from Jim Pedersen. Do you know of people that use sophisticated mathematical programming? What are the advantages or pitfalls?
I'm assuming Jim means like when we presented that optimization model, do people actually use, you know, model things that way and try to do it? There's a lot of intellectual, you know, academic papers out there And a lot of good work has been done at MIT, for example, and they use something called dynamic programming, being one of them, to optimize inventory across hierarchies. And I think some of the software that's actually out there uses some of these sophisticated techniques. And it's usually not known to the user exactly what the algorithm is, and they have faith in how it works and how it goes. But you really have to make sure that the data is deadly accurate and the model actually applies. I think it's so hard to get the equations for some of these things that you're better off starting off with something simpler and knowing the concept of this multi-criteria optimization and then maybe working your way towards more sophisticated models. So I think there are people that actually use it. My background is in fast-moving consumer goods, and I think if you do, you don't necessarily have to use that, have the concept in your mind, and you don't have to necessarily use that level of sophistication necessarily if you've managed your SKUs and you have good portfolio management in place. Next.
It looks like that is all the questions we have, Mark.
That's it?
That's it.
In explaining everything brilliantly or boring everybody to death or maybe eating into their lunch hour. Well, let me just wrap up with a few things. Please join us for the final part of this series on supply chain physics. Next time we're going to talk about, on January 20th, we're going to talk about strategies for communication and improvement. We laid the groundwork here for what supply chain physics is, the trade-offs, the laws. How do you then use them and navigate the world where you're trying to be a good business partner and dealing with the categories of violations that we just talked about, that which maybe can be done and those things that can't be done at all, and how do you use that information to create opportunities for improvement in the organization across functions. Lastly, a little bit of marketing for Cadent Resources Group, LLC, our company. We're a company that focuses on inventory management as our primary purpose in life. As stated earlier, if you remember three things about us, is we help companies reduce inventory, improve service, and generate cash. And we do that through the use of our DemandCaster tool and our expertise in supply chain. And here's some contact information if you'd like to reach us, and we're happy to do a 30-minute phone assessment of your business. So you can call Ara Serenian or myself, Mark Gavor, at the toll-free number, and you can email either of us there. We encourage you very much to go to our website, www.demandcaster.com. These webinars will be on our events page. You can watch them later, or you can have other people look at them. We have a rather extensive blog that you can look at, and we have very readable, easy-to-understand topics. And then you can follow us on Twitter. And that is it for today. I thank you very, very much for joining us, and it's been a lot of fun for me, and I hope you got something out of it as well. We would love to get your feedback. Thank you very much. Jolene, anything else?
No, I think that's it. Thank you all for joining us.
Thank you.